Okay, so hello everyone, and welcome to another session of Grant and Seminar. So it's my pleasure to introduce today's speaker, who is Anant Narayanan, who is an NPSC student here, and he'll be talking about constant curves, curves of constant width. Sorry. What do you?
So, yeah, as the title suggests, I'll be talking about the so-called object curves of constant width. I personally came across this a while back in some quantum magazine article, and yeah, I found these objects really interesting, to be honest. And yeah, the idea is to introduce you to them, and perhaps along the way, I'll give a very hands-on concepts and key objects from convex geometry. So yeah, so with that goal in mind, I'll basically start by giving some motivation about why I'll be looking at these objects, and that comes from an article by Victor Klee in 1981. So Klee talks about a variety of problems in convex geometry, a very intuitive view of problems in convex geometry in that article. And one of the problems, mostly he deals with problems involving convex sets. And one of the problems he deals with inspires this curves of constant width. So first I'll tell you what Klee thinks of convex sets as. He has, so for Klee, intuitively a convex set won't have any holes, because if it has a hole, then you can always find 2 points and then the line joining them is not inside the set. But another thing for Klee is that the set can't have any dent. If it has a dent, then again you can find 2 points such that the line segment joining them is not in the convex set. So this is some sort of concavity for him, that you have no dents and no holes when you're looking at convex sets. Now the problem that one of the problems that Klee considered in this article was the problem of house on wheels. So the problem is very simple to state. You have this. So when I'm drawing it, it's a ugly looking house, but yeah, a nice looking house. So you have this house, you have this surface here. Now you want to slide this house along this surface, and you want some sort of, you want wheels here basically, and you want to know what cross section of these wheels will work, like to allow this smooth movement of this house along this surface. Now let's start with the ones that we talks about as not convex. So suppose I take this particular cross section of the wheel or roller, which has a hole. Now, this is a very intuitive way to think about it, so there's no need to get into physics of this. But the idea is this: there is a loss of strength in this convex set. And this is not a convex set, but you have this hole here. So this is causing a loss of strength, which is not ideal for a roller or a cross section of a roller. So we discard this. Another option when we talk about the non-convex sets is this one with the dent. But if you have a dent, then once you roll this house along this particular object curve, then you'll have this dent will either cause the house to get stuck over here, and which will hamper the smooth movement of the house along this surface. So you discard this as well. Now we also consider the fact that there are some like sensitive items inside this house. Maybe there's a 2-year-old inside, so you don't want the house to go up and down like a lot. So you want something convex, but you want further restrictions. Now, what are these further restrictions? Now, let's say, this problem. Now, suppose I have this particular convex one, an ellipse, but a very so an ellipse that is thin over here, but rather thick when you look at the the major axis. So what's the problem here is that once you start rolling, so when this rotates basically, then at some point you'll have this minor axis being horizontal, the major axis being horizontal to the surface, and at that point the house will move down. And similarly, as you move forward, at this position it will again go up. So there's a lot of up and down movement, which is not ideal for this smooth movement along the surface. So you don't like these objects here. And similarly, if I take a polytope here, this particular polytope here, same problem. As I move along, rotate this, a lot of up and down movement, which is not ideal.
So first you were saying about non-convex body. Now you're talking
about
convex.
I want some. Now, so the point is to allow this forward movement without a lot of up and down movement, you want some sort of consistency. If I'm thin, I would rather be consistent. And if I'm fat, I would rather be consistently fat. So that is the idea here, that you want convex sets that are consistently thin, and that's where the title, informal title, that came from, consistently fat. You want your convex bodies to be dense. Okay. Now, another way of formalizing this is saying that the convex bodies have a constant width, meaning along each direction it's either constantly thin or constantly fat. So to formalize this notion, okay, actually, before formalizing this, of course, the practical solution would be to have a circle as a cross section, because there is consistent width. So since you have if you have a circle as the cross section of the roller, then you're fine. But because this is a mathematical, it is a partially practical yet mathematical problem. So you also want to look at non-circular answers to this. Do I have such certain other convex shapes that will act as cross sections of these rollers, which will be suitable cross section for these rollers? So yeah, so this is the question. Are the non-circular convex shapes of, I'll say, constant width here, which I'll formally define first. But for now, I think this is fine. And I think that is this problem of finding this non-circular convex shape of constant width. Again, I'll define this formally. Came from actually was Euler started studying these objects back in the 17th century and 18th century, and then in the 19th century, one of the objects that he came up with actually gained prominence because the German engineer Franz Relu, he used these objects in designing certain motor engines, and that is why these objects came into prominence. So, yeah, before getting into that, I'll formally define them now. So you take convex body, K, then R, D. Sometimes you restrict ourselves to R2 to make for ease of explanation, but I'll mention it when we can actually generalize something to RD very easily. But for now, take a convex body K and RD, and now for us, a convex body is convex, compact, and for convenience, I'm taking non-empty interior as well. Non-empty interior. We have this convex body. Now, because this width, as we'll see later, is actually a very translation invariant notion, and what you'll have is, let's say, without loss of generality, you have the origin inside here. To define the width, you actually have to look at the direction. Now you fix a particular unit vector, let's say u. Now along this direction, you want to find a supporting hyperplane which has u as its unit normal. So I'm moving along this direction and I'm finding let's say, supporting hyperplane. Now similarly for minus u, I'll go in this particular direction, and again I'll find some unit. Okay, yeah. I'll find the supporting hyperplane, which has minus u as the unit normal, the u as minus u as the unit normal. Now, these supporting hyperplanes will in fact be parallel. These supporting hyperplanes that you have, they are parallel, and the widths in this direction u. This is simply defined to be the distance between the supporting hyperplanes. So, for any convex body K, when I talk about width, I'll specify direction u, wk of u. So along for each unit vector, you have this width. Now, when I say consistently fat, consistently thin, or constant width, I simply mean that wku is independent of u. That this wku is a positive constant for all u and s d minus. Yeah.
So that's WK is basically the convex analysis studies the supporting function.
It's a support function. Yeah, I'll come to that. I'll come to that later. Yeah, but precisely, it's the sum of the support. So it's the support function for u and for minus u. You add them. Evaluated at u.
Being support function is being constant basically means you get the ball.
No. The sum of the support function is constant. HK of u will give you this. When you evaluate the support function at this unit vector, it will give you this distance.
Right.
And for minus it will give you this distance. So basically the sum is constant. They are not individually constant. So HK of u plus h. So if the support function is HK, then HK of u plus HK of minus u is But I'll get to that. That's a very good point. So yeah. Now, so of course, a very simple example of this is what? A curve. If I ask you for a curve of constant width in R2, what is that? In RD, let's say. Ball. Correct. So you have ball, and what is the width in that case? Huh? Diameter. It's a diameter. So very simple example is yeah. So yeah.
Can you give an example of convex body which interior is
Convex body whose interior, convex body definition I'm taking non-empty interior.
No, but if you are taking that, it means you are saying that some might.
Yeah.
Hard to. Okay.
No, I'm just basically I just don't want it to be a one-dimensional problem. Let's say you're in 2D, I just don't want it to be a one-dimensional problem. You can of course take any one-dimensional convex body now. Yeah. So yeah, now what we'll do is, so we have this general definition for RD. So a curve of constant width is basically this width in every direction is constant. Now, ball is one example. So we'll return to our question. Are there non-circular convex shapes of constant width? And for this, we'll start with R2 because yeah, we are motivating this construction from R2 is actually very beneficial for us. And as I said, it started with Euler and went on to this German engineer, Franz Relu. And Relu, the objects that we'll now define, they are named after Relu. And I'll start with what is called the Relu triangle. So Relu triangles are basically the simplest and best known examples of curves and shapes. So curves and shapes are used them interchangeably. Curves and constants. Simplest, we'll see it's basically in terms of construction because when you go to higher dimensions, the construction becomes very, very difficult. So simplicity is in terms of the construction, and best known, I'll get to that. Best known is also a very interesting phenomenon that happens with these two triangles. So the construction is as follows. So as the name suggests, triangles, we actually start with an equilateral triangle. Does it look like an equilateral triangle? It does. So you fix this vertex. Now for this vertex, you look at the circular arc. So you look at the circle with these two points inside or on the boundary. So on the surface. Now you look at this particular circle arc, and similarly for this particular vertex, you look at the circle. For this particular vertex, you look at the circular arc joining these two. You can do this because this is the equilateral triangle. So now, so basically this entire region that you have, that is an intersection of convex sets, three convex sets. So this is convex. Now, why is this a curve of constant width? Because now for curve of constant width, you have to look at parallel supporting hyperplanes, right? You take any circular arc, fix this circular arc. If let's say I take this supporting hyperplane here, a parallel supporting hyperplane will correspond to a supporting hyperplane for this vertex here. So you'll have this. Now the distance between them, this is the circular arc. So the distance between them is precisely this distance, which is the side length of this equilateral plane. So if you take any supporting hyperplane here, the parallel supporting hyperplane will lie here, and the distance will be the side length of the equilateral triangle. Now similarly, if let's say it is very much possible that you have a supporting hyperplane here and consequently a supporting hyperplane over here. But in this case as well, the distance is the side length of the equilateral triangle. So in case of the Relu triangle, and because we've done it for this particular vertex and this circular arc, it follows for all.
Now some different points than just the vertices.
Sorry?
How about some two different points which are not vertices? Let's say in the middle of those two.
As in here, you see. No, over here.
Yeah.
Here.
Yeah.
So that corresponds to this case, right? The circular arc. I'm taking a supporting hyperplane here.
Right.
There it will correspond to this particular. Now, so yeah, so Relu triangles are curves of constant width, and the width is precisely the side length of the underlying equilateral triangle. Now, so this is a 2D construction, but like I wanted to ask you guys, so is it, well, can you suggest some method of constructing it in 3D? Like what is the natural way to construct a curve of constant width in 3D from surface of constant width in 3D from this construction? Tetrahedron. You take a regular tetrahedron, and over there you consider these, again, you consider these balls and you take the intersection, you'll get some shape. and that is called the that is called the root tetrahedron. But we haven't really established the fact that this is the surface of constant width. So this for now is a candidate. I'll tell you, but I'll give you a spoiler that there are many bodies of constant width in higher dimensions. There are very general constructions. But for now, I would like to think of this object and we'll just treat it as a candidate for now. I won't really tell you if this is one or not. We'll keep that for you. So now, yeah. So there's one more thing over here. If you look at this yellow triangle construction, can I do it for any other n-gon? What is being used here? You have this particular side length, equilateral triangle. You are using the fact that there is a notion of an opposite vertex here. So if I'm taking this circular R, this distance is preserved as I'm moving along this. So can I generalize it to any other n-gon? What do you guys think? Is there any infusion here? For 3-gon, I'm doing it. Every odd. So like, let's say I'll take a pentagon. Okay, I have to draw a good pentagon. Oh, God. Yeah, good on, Good. Yeah. Okay. So you have this pentagon, regular pentagon. How will you proceed here? So like similar to the construction there.
Take the sides.
So you take this particular vertex and then this side you're saying. So you consider a circular arc over here. And similarly for this, you do the same thing over here. And you go on. Basically, again, intersection of circles will have. Intersection of circles will give you a ReLU 5-gon. But again, why is it working? It's working because you have this notion of opposite vertex here. If I look at this vertex, if I take any supporting hyperplane here, it will correspond to a parallel supporting hyperplane over here. And then the distance, again, because of the circular arc argument, will just be this particular. And again, if I start at this point, it will be this particular length. If I start at this point, it will be this particular length. But because you're considering a regular 5-gon, these distances are equal. But you can do this for any 2 plus 1 on this particular construct. Now the question is 2n-gon. What's wrong there? I mean, so we were trying this actually a while back. We were trying this construction for 2n-gon. And yeah, the basic problem is you want this notion of opposite vertex, and it's not really clear how you would proceed. And we were actually able to show that you can't actually do it. You can't follow this construction for the square or let's say a 6-gon and so on. But the interesting thing here is that there are many other methods you can use to construct these constant width bodies. Yeah, and yeah,
Status square.
yeah. Okay, let's try.
Take a midpoint of one side. Yes. Now draw that for the yes.
Okay. And okay, the thing is,
And you keep doing that step.
yes. Okay, let's say I have so for this, okay, for this particular, you're taking this curve, this particular curve. Is this a curve of constant width?
Can you see that?
Over here, if you let's say you actually we're not figuring out, yeah, but over here, if you take supporting hyperplanes, the distance is the diagonal length. Right. But let's see.
Same argument should work. You have a point.
Let's see. This
Can you repeat what was the argument over there exactly? How did you prove that these are curves?
yeah, so like if I take a supporting hyperplane over here,
Yeah.
your parallel supporting hyperplane will pass through this vertex.
Always. Yes.
Yeah, for this one, it will always pass through this vertex.
Okay.
And then this distance is because this is on a circular arc, this distance will always be the side length of the arc.
Say that.
Yeah, here you will take a sort of parallel to this sort of x-axis.
Okay.
Very like the south pole.
Ah.
Then what will happen?
You'll take this.
What is the opposite?
Parallel.
Parallel to that will be
So-
something like that.
Yeah.
And that is not the same. I think that will be the same, right? It's not the same.
Yeah.
Oh yeah, because this distance is the diagonal.
Yeah.
This distance is the diagonal, so this is more than the diagonal. That is not diagonal. No, this is not the diagonal line. This is more than this. This particular distance is the same as this particular distance. Yes. And I think okay.
Right.
It's not
Yes,
diagonal.
that is there.
No. But that's diagonal. Right? Yeah. Could happen that this is equal to the diagonal. Can it happen? Yeah, it can happen. It can.
Can, but I see it. I mean, you can calculate it, but
Okay, I think go ahead. Yeah. But actually, I wanted to get to the fact that there are other constructions. So not necessarily you don't follow this construction, but could very well be. I'm not even like denying it at this stage because I'm not too sure. But in general, for irregular polygons as well, you can actually construct these bodies of constant width via some construction. So there is this magician and mathematician, both Martin Gardner, who called certain methods called crossed line methods, and he actually I don't know if he proved it or he just named these methods to be cross-line methods. I don't know why. But yeah, he actually, whoever did it, they showed that you can actually construct these bodies of constituents from any from certain irregular points. Not necessarily all, but some. So yeah, again, very good possible. Now, I would definitely like to mention here that the Relu triangle that you see, this is actually if someone plays the guitar, this is actually a guitar. This is exactly that. If you have played the guitar, and actually, is there a reason why? Yeah, I think it's basically constant with whichever way you hold it. I don't know precisely. I think that's the reason. Whichever way you hold it.
But then why not circle?
Huh?
Probably there's something else. No, it's easy to.
You cannot pick this.
Yeah.
There's no sharp. So also this for this 7 gun, so the heptagon, the regular heptagon, the corresponding Relu polygon, that's actually the 50 pence coin that the British 50 pence coin. That is actually a Relu heptagon. So these you will actually, if you can actually look at these obviously if you want that. But yeah, now right. This okay. So another textbook question is: I have this yellow triangle, I have this yellow polygons. I'll solve them now. You have these polygons. There is something common in all of these examples. Something that let's say look at the vertices so far. There is something common with all these little polygons. What is that? Just focus on the vertices of the polygon. There is no smoothness. So this lack of smoothness, so one naturally asks, other than the circle, we have proved there are non-circular convex shapes of constant width, but are there any C infinity ones or smooth ones? Now the answer to that is a resounding yes. Ouch. Yeah, the answer to that is a resounding yes. And okay, so perhaps even in the Relu polygon, there is if we carry out a certain smoothing over here, and over here, one has to be really careful because we were relying on that circular arc argument. But if you are able to choose your smooth functions wisely, I think that can be done. You can actually make smooth convex bodies of constant width from these Relu polygons as well. So the reason I said resounding yes is because of the fact that if you take this is true in RD as well, but I'll state for R2 because in R2 something more specific happens. If you take any curve of constant width, this can be well approximated by smooth curves of constant width. So in the first of it, so in the epsilon neighborhood of every curve of constant width, you'll find some smooth curve of constant. You'll always find some smooth curve of constant width. And in R2, the special thing that happens is that the smooth curve, if you, let's say the curve of constant width, that's your target, let's say it has width 2, then you can always approximate it by smooth curves of constant width 2. You don't even need to change the width. You can always, the width may remain the same. In RD, I'm not too sure about this, but in RD, this density like is 2. So you can always approximate your body of constant width by smooth body of. So yeah, this is the C infinity case, and if anyone wants, like, I've written down certain references here which I'll share. So there are many standard procedures to construct these convex bodies of constant width. And so there's a paper by Robert Tennyson, which is actually titled Smooth Curves of Constant Width, and this is in 1970s. So I'll just call it SCW. And there's another paper by Schneider, Rolf Schneider. He's the one who defined this convex approximability, vortex approximability, and all these things in 1985. So his paper is called this smooth approximation of convex bodies, and here he mentions this density language that your bodies of constant width can be approximated by smooth bodies of. Okay, good. How are we on time?
And
Yes, yes, yes.
so when you're taking this sort of circular arms,
Yeah.
are they sort of uniform width or like you can take a very big
No. In this case, because it's an equilateral triangle, so this is
but you're taking the best fit sort of thing.
yeah. Yes. I'm taking a best fit. Yes, correct. So
I was asking circle I'm not taking of a circle. The best fit circle
Vertex and radius the equidistance.
that's it can't go inside. Best fit in the sense that it's
It's not a circle.
That's what makes the sheet.
It is not a circle.
It's not a circle.
yes. It is a circle. It's an arc of a circle. Yes. The whole thing. No, whole thing is a circle. This is a circle. That's what I'm saying. This is not a circle. Yeah. Okay. Yeah. It's basically this is something like that. Actually. Yeah. It's not a circle. So, any other questions? So, what we'll do now is like we have a lot of examples now, and you believed me.
We have a lot of different curves which is constant.
Correct.
Then there's some areas between them, like
The area they enclose,
Yeah.
that is, we'll get to that. Beautiful. We'll get to it. So that's actually going to be what we are studying like in 10 minutes or so. That's going to be what. Now what I'll do is actually we have a lot of examples now, but when you look at this class of bodies, I call it a class because we have many examples. When you look at this class of bodies and you want to ask certain questions like the one Satyadarshi just posed, let's say I'm taking all curves of constant width, which one encloses the maximum area, let's say. If I want to answer questions like these, it's always useful to have some operation where these objects are nicely. So what I basically mean is, let's say I take a body from this class K1, I take another body from this class K2, some operation I want to do so that I get a body K3 in the same class. What is this operation? Convex geometry, and actually think of Minkowski sum. So if that is defined as, for those who are not aware of this, A plus B is simply the set A plus B where A belongs to A and B belongs to B. So if A and B are convex bodies, A plus B is also a convex body. And what we show now is that this class of bodies of constant width, they behave very nicely. And for that is okay. Let's see. Is it for anyone? Is it intuitively clear why that might be the case? If I take a body of constant width, I take another body of constant width. Even in R2, there some will be a body of constant width. Is there any geometric intuition for this?
The support vectors are just active.
Huh?
The support vectors.
Yeah, that's okay. Yeah, you actually. Yeah. So yeah, it's exactly. Yeah, the reliance is actually on the way you define support function. You can't just directly geometrically look at this and say.
Take a constant width. So A plus B basically at each point you
At
are
each point of it.
attaching a copy of
Correct.
B.
Correct.
So it's sort of a patterning of
Correct. But now, correct, but you're also looking at hyperplanes, so that makes it a bit more complicated, right? How are the hyperplanes of A plus B looking like? That's not too clear at this stage. But exactly. Yeah, so the reliance is actually on the analytical way you define this width, which is what Nemo said, what Vikira is saying right now, is in terms of the support functions. So you take any convex body K, again, for those who are not aware, I'll define all of this. Let K in RD be a convex body. It can be done for any closed convex set as well, but yeah. Sorry. So to define, so for each y and RDs, for each y and RD, you define HK of y as the supremum of overall is in a product of k of y, it should make this k, k belongs to k. Now, what is this telling you? So, a nice way to look at these things is by looking at unit vectors. So, if you take u and s1, this is basically telling you how much. If I start at the origin, let's say your convex set contains the origin. If I start at the origin, move in the direction u, how much can I move before I hit the boundary or reach the supporting hyperplane, which has u as a unit normal? So, let's say this is my convex body k. I start at the origin, I move in the direction u. It's basically telling you the distance of this supporting hyperplane here from the origin. And similarly, if you're doing it for u, you can always do it for minus u, which will basically give you the distance for this particular supporting hyperplane. Now, what is width? Width is this particular distance plus this particular distance. So, if you want to define WKU in terms of HK, that will just be HK of u plus HK of. Correct? Now, bodies of constant width, this quantity is a constant for some alpha greater than 0. So now, to basically answer these type of questions, it's very useful to think of support function in this case, and in more generally as well, because directly thinking of it geometrically might not be fruitful many times. So having this sort of definition and these sort of objects and this sort of a definition proves to be very fruitful. So what you basically have as the definition of constant width right now is that if I take a support function and writing any unit vector, then it's ku plus it's k of minus u is a constant. Okay, now it's going to be particularly easy to look at this Minkowski addition thing, because if you take h of k1 plus k2 of y, that will just be h of k1y plus h of k2y, hk2 of y. So what's happening is that okay, I'll just take the properties there. So if I take h of k1 plus k2 of u, that is h of k1 u plus h of k3 u. Okay, this is second best. What this is telling you is that if I take the one body of constant width, another body of constant width, this Minkowski addition is the body of constant width, and the widths just get added. Another nice thing about these support functions is that h of alpha, alpha is h of c k u. This is x u for all c. So if I'm scaling my body, then the scaled body is also a body of constant width, and the width simply gets scaled. Finally, if I take h of minus k of h minus k of u, that is hk of minus u. But again, because our definition involves both hk of u and hk of minus u, there's some. The width of minus k will be the same as the width of k. So minus k will also be a body of constant width and with the same width. So it's is a body of with the same width. Now you have these very nice properties. Now you know a lot about these bodies of constant width through these support functions, and that is very useful for us. Right. So up till now, are there any questions as such? Nothing.
I have one.
Oh,
So if the body is central symmetry,
yes.
so automatically becoming constant weight means its cycle time is called.
So yeah. So we have elements. So the next exactly what I was said. If you have a centrally symmetric body of constant width, it is precisely a ball. And more generally, what you'll have is, so if you have K in RD, then K is a body of constant width if and only if K, the Minkowski sum of K and minus K is a bond. Very sweet little characterization. If K is a body of constant width, K plus minus K is centrally symmetric and it is a body of constant width, so it has to be the ball because your support function is constant. If this is the ball, you basically use the fact that this is allowed to take the value. These are defined for extended reals. So, and the width of K and minus K is the same, so the width has to be finite. If K plus minus K is a body of constant. Sorry, the width has to be constant. If K plus minus K is a body. So you have this very nice characterization. And this is like pretty useful to be honest, very, very useful. And like more particularly, what you have is K plus minus C is just false and at 0. And what will the radius be? It's the width, it's the what? It's the width. So which is alpha. It's the width of K. Correct? And this will be very useful in answering questions, the question that Prativashi asked. So that's what I'll move on to now. You have this class of bodies, you have a very nice operation under which these objects interact very nicely. You have this beautiful characterization which tells you about this combination. If you take the combination of K with its reflection, that is a ball, which is very strong according to me. And now we use this to answer certain questions that we might. Yes. I started at 20, right? So 20. So now we want to learn more about this class of conflicts, constant with bodies of constant width. Now we look at some isoperimetric type. So when you deal with convex bodies, you have this very nice thing. You have this very natural question: is if that I fix one aspect of the convex body, how is the other aspect behaving like? What are the maximizers of the other aspect? What are the minimizers of the other aspect? And the same question you can ask over here. There you, so let's say you're fixing some curve in R2, simple closed curve in R2, which encloses the convex set. You might ask, if I fix the perimeter, what is the largest area that I have, which is precisely the classical isoperimetric inequality. Same thing I can ask here, but now I have a very natural candidate to fix. What is that? Width. So I fix a width. So if I consider bodies of constant width of a given width, basically of a given width W. Now with this, so we'll actually be moving between R2 and R2. So I'll tell you when we do that. But for now, let's consider this in RD itself. You can ask two questions here. What's the, actually let's stick to R2. You can ask two questions. What is the maximum area of the convex shape that you have with this, for all convex bodies with this given width? And what is the minimum area? Pointer. This is precisely, okay, what do you expect this to be? Oh, this is what we said. This is true more generally in RD. And what do you expect this to be? Very complex. And that is why I call them the best known bodies in dimension 2. Because these act as minimizers of this very natural question that you might have is they're really and this is an R2.
In RD,
RD, okay. In R3, the resolute tetrahedron we constructed, I'll get to that. So in R3, nothing is known. But you have conjectured minimizers, but you don't know whether the minimum area corresponds to them. Well, that is minimum area. You don't know that. In RD, you don't even know about the minimizers. because the objects are very hard to construct. So you don't even have any indication that this might be the value. For R2, you this might be the value because you have some conjecture minimizer, but not proved at all. So R3 and higher dimension, this is not proved. This is completely done in RD. And first we'll focus with this particular problem of maximizing area. Where should I go?
In R2, the value lines, they are unique.
Sorry?
R3 only primary.
Yeah, so under rigid transformation, translation, rotations, reflections. Yeah. And simplex. Okay. The D simplex. Okay. As what? No, the tetrahedron, the body you construct with the tetrahedron. Yeah, the point was you have to construct a Relu polyhedron using that tetrahedron.
Marcel, we don't know that.
We don't know that. So for the tetrahedron, you may carry out the same Relu construction, but you don't know if it's a body of constant width yet. I have not told you if that's a body of constant width. That's I have not told you that, but you are very close by that in terms of minimizers. That's where those minimizers actually come from. But okay, not exactly that. I'll come to that soon. Okay, so is it fine if I write here? It's fine. Maybe that should go.
So let's say you have one body with constant width in RD.
Okay.
Let's say slice it with. I mean, if you take a slice.
Okay.
Body with constant width.
If I have a body in convex width, if I take a slice, will it be a body of constant width? I think yes, it should be. It should be yes.
Like
Cut it. The cross section, will that be a body? The cross section, will that be a body of constant with an RD minus 1? Should right, because you're taking all supporting hyperplanes, so you can take supporting hyperplanes corresponding to those points as well.
yeah.
Huh? Two dimensions of the circle. What is the slice? So I think that should be
Just that one.
cross section. Cross section.
Okay. I was thinking, what is wrong with triangle? That can be.
I think that should be. Yes. And then you look at the industries, what that does, and that's a curve of constant width. Yeah, in a ball you will get it. But let's say you have something complicated.
We haven't done anything on higher dimension.
Yeah, because of them.
Yes.
Right. Slice is any plane or like some particular plane? Just cut it with any plane. Around the axis.
Yeah,
There should be the axis of symmetry.
so we don't have enough examples in RD.
Exactly. But yeah, that's another point. You don't have very nice looking examples in our RD D greater than equal to 3. So that's why it's a bit tough to imagine that. But perhaps
In common, sorry.
get back to it. So I have to erase it. So yeah, the tool that so I told you that I'll be giving a very hands-on approach to certain inequalities from convex geometry, and what we use here actually relies on this particular fact here. You know what K plus minus K looks like. So you know what the volume of K plus minus K is like. You know the volume of K is the same as volume of minus K, and you also know what the volume of K plus minus K is, the Minkowski addition. So is there some sort of an inequality that can, let's say you have some bound on the combination of convex bodies. Can you say something about the original component convex bodies? And that actually comes from that's actually comes from Minkowski inequality. Inequality. It deals with exactly these scenarios. Where you know something about the calculation, but you want to know about the components. And so I'll be stating it for convex bodies in general, but it's true for measurable quantities, sets, or more generally. But what you have is, it basically says that the logarithm of the volume is. So if I take for lambda comes to 0, 1, if I take AB to be convex for these, then the volume of lambda A plus 1 minus lambda B is greater than equal to volume of A to the lambda, volume of B. What is log concavity here? Basically, you take the logarithm both sides. This is log of volume of lambda A plus 1 minus lambda B. That is greater than equal to lambda times log volume A plus 1 minus lambda times log volume of B. So the logarithm of the volume is concave, is what it's saying. Now we know about K plus minus K, right? And the nice thing is we know something about the width radius of the ball as well. It's in terms of the width. So if I do that over here and given K with what was the width, W or alpha? What did I take? The alpha. So let's say of be consistent. That's it. It's alpha. So if I take a convex body with alpha, then basically take A to be K, B to be minus K, and take lambda to be 1 by 2. Then, yeah, what do you have? So you'll get that volume of half of K plus minus K. The brackets are fine. This is greater than equal to. So volume of K to the 1 by 2, volume of minus K to the 1 by 2, volume of minus K, volume of K. So this is volume of K. K plus minus K is the ball of width K. So this is basically the volume of the ball centered at the origin of radius alpha by 2. Correct? Where alpha is the width of K. So this is greater than equal to volume of K. Now this is what? This is precisely the Euclidean ball of with alpha. And we're saying if I take any convex body of with alpha, it is the volume is bounded by this. So you get that balls are maximizers. But are they the only maximizers? How do we show that? The way you do that is basically looking at this, the equality for the Brun-Minkowski. The equality for the Brun-Minkowski holds when A and B are homothetic. So in particular, when K and minus K are homothetic, which simply means that minus K is from A K plus X, where A is constant greater than 0 and X belongs to RD. But okay, translations are fine. I'm fine with translations. But what can A be? If you look at this support function here, if I take any other constant, if I take a constant other than 1, the width will change. But the width of minus K and K is the same. So A has to be 1. So basically your K has to be symmetric about some point. Symmetric about some point, body of constant width. We show that it is a ball. Basically, the argument that Ignivo gave. So K has to be a ball. So this implies that A is equal to 1, implies that K is a ball. And this is how you show that balls are the only maximizers of the volume of the area of the volume when you consider volume. I have 5 minutes, so what I'll do is for the okay, I was anyways not oh.
You have 10 minutes.
I have 10 minutes.
Yeah, that is fast.
Oh no. Okay, so this sorry, YouTube, but volume of K, you take any body of constant with K, the volume of K is bounded by the volume of the ball. Now, yeah, of course, I will ask this particular question. Now I know that volume of K has the volume of the ball. This is the ball of a particular radius, which is the width here, fixed divided by 2. Now this is less than equal to 1. This is what you know. This is actually a quantity which is called the effective radius. And first, well, I don't know the exact reason why it's very important in the supporting geometric analysis, but that is the case. And what people are interested is in how far is this K from B? Like, can I instead of 1, can I give some other bound? For a fixed width, can I give some other bond here? Is that possible? Let's say I take all convex bodies of width 2, right? So I know volume of K for any convex body K of width 2 divided by the volume of the ball of radius 1. That will be less than equal to 1. That is clear. I'm saying, can I do better than 1?
From that.
That's from that. Can I do better than 1? That is the question. And this is very recent work by Nazarov and co, where they actually, this was a question posed by Uday Shram, I think that's how it's pronounced. And he posed this question as a graduate student at Princeton in 1988. And he basically, what he asked was, does there exist an epsilon in 1 such that for all let's say for all convex bodies does that there exist convex bodies of constant width. So he fixed the width to be 2. So but that is not a constraint. You can do it for any width of constant width 2. Such that so he wanted the sequence of convex bodies Kn, where n is greater than equal to 2. So you want Kn to be in Rn. You want Kn to be a convex body of constant width 2. And the question he posed was, can I find the sequence such that, can I find an epsilon and can I find a sequence such that volume of Kn by the, so for Kn you look at the n-dimensional ball of radius 1. This is big O of 1 minus epsilon to the n. This is what he asked. So from can I make it better from 1 to this 1 minus epsilon to the n? And this is what Nazarov and a lot of people from Manitoba, I think, they proved this very recently in September 2024. They actually proved it for epsilon is equal to 0.1. So yeah, so they showed that this is big O of 0.9 to the n. Which is of course a much better, bigger improvement from 1, but not. So this is what they proved. So this is some sort of a bound on the effective radius for this given sequence of points. Okay. And yeah, so very recent work, and actually they are still interested in these objects. And as I said, because you don't have a lot of nice, you have a lot of nice constructions, but it's still very hard to compute the volume when you look at these constructions. It's not so clear. So having very, let's say, easy to look at constructions which tell you about the volume is still very important in this. Looking at answers to this question. Can I make this better? In what sense can I make it better? And of course, to answer those isoperimetric type problems as well, people are looking at those questions in higher dimensions, and even in settings of not necessarily the Euclidean space. Let's say Riemannian manifolds. They have certain. There's this paper. I'll write it here. Width of embedded circles. So I don't know the exact what exactly they've done here, but they talk of Riemannian analogs of plane curves of constant width in this setting, in the Riemannian setting. So this is a paper if you're interested, you can look at. And for the minimizer, I should say something, right? Relu triangles.
Yeah.
So for the Relu triangles, yeah.
Yeah, but it's not a strict like whatever you want. You got a sequence for which this is true.
Yeah.
But not for every.
Yeah, not for all.
Even the one is not like you told that it got better, it got to 0.9 power n.
Yeah.
That is something like for a sequence.
Yeah, that is for a sequence, but you still, that's what I'm saying. In higher dimensions, you don't even know for, like, there are not many clear examples of bodies for which you can calculate this volume explicitly. So to have these examples where you can actually talk about the volume and you can actually give a bound on the volume, and hence the effective radius of these objects is actually very interesting to them. And so for them, it was also a matter of constructing these in higher dimensions, which they were able to do. And the construction was actually a modification of the construction of the Relu triangles and so on. You have to do certain clever things. I'm not particularly sure about them, but yeah, it's a modification of that. And yeah, they were interested in certain objects. No, you can't do it for all. But for all objects would be unreasonable because
or like to constructed this triangle by taking three sides.
Yeah.
I can take 2n plus 1 and construct such things.
Correct.
I can increase my n. Okay. Somehow that will tend to a circle and stuff.
Okay. Yes.
Those things are tending their areas towards circle only in 2D.
Yes.
So just think like 1 is the perfect because I can increase my n to infinity and then construct.
No. Kn is in Rn. The dimension is changing here. Kn is in Rn. It's a dimension in variant sequence. So the dimension is changing.
So I'm talking about in 2D only.
Uh-huh.
To say that I have a ball.
Yeah. In 2D, the best is the ball, right? So you have a convex body for it.
The strictness of one cannot be.
Oh yeah, definitely not, because you have the ball.
No, but like
Even if you don't take balls, you're saying.
Yeah.
Yeah, correct. You can be as close to the ball as you want. Yes, correct. That is true. Remove polygons, right? Because
No, then this question doesn't make any sense. If you're saying this is the perfect bound.
oh wait.
No.
Oh, okay.
You're saying can it be as close? Can you find convex bodies of constant width truth that are as close to the ball as possible?
In dimension 2 is.
Yes. That is the
Yes.
question, right?
Yes, that's what he's saying.
Yeah. So if that is true, then then this question doesn't make sense.
Why?
Like if you have, so you have first started with volume of K by volume of B is less than or equal to 1.
Correct.
Then you said like, can you make it better? Does it need to be always 1? Can it be smaller?
Yes.
Right?
Yes.
So if there are convex bodies as close to B as possible.
The point was you don't have explicit examples of these convex bodies for which it's away
But
from.
you're saying they are possible.
They are possible.
They can be, the volume can be as close to.
Yeah, that should be the in higher dimensions. I'm a bit conflicted about this, but in dimensions 2, yes, right.
It's not clear.
And even in dimension 2,
Yeah. They'll go as close to circle as possible, is it? No, they are dense.
oh wait.
No, but the thing is there are too many non-smooth points. The number of non-smooth points is increasing. And that
But the volume is approaching the volume of the
Yeah.
flowers. It's like flowers.
Exactly.
But as the thing is, the volume goes to the ball.
the volume can go somewhere else.
Yeah. I think you can probably show that it is monotone as we are increasing the lengths. Probably the volume is increasing. If you show that. Yes. Suppose you show that, then as it's going there, that is unique. The ball is the unique one with the volume. So
That would be one way to do that.
yeah. And in any sense it converges, then it must convert to the ball. But it does not.
No, that is not clear. It might converge to something less than 1. Because it might be some.
Okay.
It can still converge to something less than 1.
But for volume, yeah.
Because
you're right.
they're all
Correct.
minimum thing. They're not even
Correct.
like they're oh no, they are not made. Only the triangle is true.
But you will treat it so that it's constantly.
You can always do that. That you can always do.
This is this way.
No, I think the question is, I'm not sure because it's not clear. Probably the question is this. Like, I think the another way to put this question, if that makes sense,
Which
is
one?
this
Sham question.
Huh?
This.
Not this statement, but I'm saying just this volume fraction thing.
Yeah.
Now you take set of all volumes of bodies of constant width.
Correct.
Like there will be some subset of minimum area, comma maximum area, right? There will be subset of that interval.
Correct.
Right.
Correct.
Now, how does this interval look?
Okay. Yeah.
Right. I mean, what if it is discrete? Like it can only take discrete values. Let's say, or does it have like what are its limit points? Is one its limit point? Or not? I think
these are all. Yeah. I think
that's probably the question because it's not clear that you have things closer and closer to God.
Oh, yes. And the body is always so far it will have polygon, right?
Yes.
And the polygons like
Reach circle.
converse to
But polygon, you're
changing always, right?
Yes, because the swing thing also brings along with a area polygon because it is changing.
The changing to it.
Polygon, so you have next polygon.
Yeah, you have to adjust the polygon. There's lots of change happening. I mean that there is convergence probably because it's monotone. But then the thing is, it could be converging to something not once.
But it probably you can calculate the volume is.
Yeah, probably. You can do. Yeah,
So the volume is going to one.
then it's done. Yeah, then it is. Yes.
What I think is if we are increasing the n now, the volume will decrease. What is happening, like if you have triangle, if you are taking 5 turns sigma, that will swing so that width will be constant. Okay. In that case, the same that your triangle shape that you are getting, that triangle,
This
that will contain the second part, the pentagon term. And then heptagon will contain like that.
For fixed rate,
No, no,
value triangle is the thing.
that's for the points. Like if you some see like that will.
No, but this year, the thing you have written, for a fixed rate, the minimum area is achieved by radius.
So, but intuition is coming like. It's will holding.
Okay, perhaps we'll talk about this after this. Yeah. So, yeah, to end, I'll just say that for these Relu triangles, the way you prove that these are minimizers, you use some notion, another notion of convex geometry, which is called mixed volume. And mixed volume, in a sense, also is beneficial because you have this amalgamation relationship. How does the combination look like? That is why this Grun-Minkowski, this mixed volume, all these inequalities or concepts turn out to be very useful in this case. But the problem with the convex geometric proof is that it doesn't really tell you that Relu triangles are the only minimizers up to rigid. For that, there's a very nice analytical proof using calculus of variations where they actually prove that these are the only minimizers modulo rigid transformations.
That cannot happen. Phantasm cannot go down.
Okay, you meant the volume of the Relu
Yeah. Oh, it will go down. Yeah.
Oh, that can happen below. Because these are the minimizers.
Yeah. After that,
So yeah, I think. Finally, last thing for the Relu tetrahedron, that is not a surface of constant width. I think good exercise also, but it is not a surface of constant width. What you can do with that instead is that you have these arcs. Oh, I shouldn't draw here. We are not recording this. You'll have these arcs. So for 2D, you have these points where the smoothness was a problem. Yeah, you have arcs, edges where the smoothness will be a problem. The way you deal with this is you look at a particular triplet of edges. Let's say I look at these edges which correspond to a curved triangle. You'll smoothen out these edges. That gives you a surface of constant width. And the other thing you can do is you'll look at 3 edges corresponding to a fixed vertex. You can smoothen these out. So that will also give you a surface of constant width. And these actually turn out to be the only 2 surfaces of constant width that you can construct from the Relu tetrahedron. These are called Meissner bodies. And Meissner bodies are precisely the bodies which are conjectured to be the minimizers of this particular problem in R3. Higher dimension not known at all. And yeah, with that, I think I'll end. Yeah.
why is the German tetrahedron not constantly?
Yeah, I think good exercise. Even I wanted to figure out. I had to figure out explicitly. But yeah, perhaps. Yeah, I think. Yeah, these edges are a problem here. I think over there you had these circular arcs and these opposite vertices. Yeah, but the edges might cause a problem in terms of looking at the supporting head. Means I was still figuring it out before.